Natural physics is a concept astrophysicist LeRoy developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as LeRoy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Greetings, I'm LeRoy, and welcome to the Natural Physics Experience, live from Costa Rica. Where we left off last week was trying to find out the value of that elusive K, the force constant of a quadrupole magnet in the synchrotron at Fermi Lab, okay? Now, what I want to remind you of is that we're using linear algebra, right? A tool from our toolbox, our mathematical toolbox. We're using linear algebra to use matrices to describe a physical object, a quadrupole magnet. So, to remind you of such, let me do this. Okay, here are quadrupole magnets in the synchrotron at Fermi Lab. As you can see, they have a physical length, width, and height. So keep in mind, these mathematical matrices that we've been using from linear algebra are actually simulating these quadrupole magnets, okay? A mathematical representation of a physical object, huh? How cool is that, right? Okay, and let's pull up that 4x4 matrix that we came up with from linear algebra to represent these quadrupole magnets. Okay, let's do that. Okay, here's that 4x4 matrix from linear algebra that mathematically describes the physical quadrupole magnet, okay? I don't want you to lose sight of that because I'm flinging a lot of mathematics at you, but look how cool it is that we actually have a mathematical tool from our toolbox that enables us to use a matrix from linear algebra to describe the magnetic effect that a physical quadrupole magnet has on a proton as it circulates around that synchrotron at Fermi Lab, huh? Right? Okay? Okay? Yeah. This matrix is a mathematical representation of a physical object. The effect that that physical object has on another physical object, right? The quadrupole magnet on the proton. All right, okay, so let's go. So then, what we did in search of that elusive K, that force constant, right? The force constant of the quadrupole magnet, similar to how tight or how loose the coil is of a spring, a physical spring. We're looking for that constant K. So what we did, we split that 4x4 quadrupole magnet matrix into two 2x2. Okay? And then, this is review, and then we applied the thin lens approximation, which you can see how much that simplifies things, okay? Now, what we're going to do, now that we have applied the thin lens approximation to the two 2x2 matrices that we got from the 4x4 matrix, okay? Once we get that, now what we're going to do, okay, you ready? Here we go. Because we're talking about a thin lens. Remember, it's a mathematical concept from optics, where you could take a physical glass lens and grind it down to where it's a thin lens, which really doesn't have a physical dimension. I know that's kind of funky, right? But hey, right? Whatever works. So imagine, call it a filament, right? Like a filament, smoke or something, right? So a thin lens, it has the properties of a lens, but without having a physical dimension. So that's what's used in high energy physics with synchrotrons to try to get an idea of what the force constant is. That concept from optics is used in high energy physics. Huh? How cool is that? Okay, so because we're dealing with, let's go back, because we're dealing with a thin lens approximation where you have one 2x2 thin lens matrix, which is representing the radially focusing in the horizontal direction of the quadrupole magnet. And then you have the other one, which is axially or vertically focusing. Let's just, another quick review. Let's go back. Here's our 4x4 matrix, okay? A quadrupole magnet, right? And in this case, it represents a radially focusing in the horizontal direction and a vertically defocusing in the vertical direction, okay, on a proton, all right? So when we split this 4x4 matrix into two 2x2 matrices, this is what we have. So this 2x2 matrix represents radially or horizontally focusing and axially or vertically defocusing. And this matrix represents vertically focusing, axially focusing, or radially or horizontally defocusing. So the two elements, okay, have been separated. And then the thin lens approximation is applied, okay? And you can see how this simplifies matters very much. Now, all right. Remember, these are theoretical constructs. And you know how I want to use that word. These are mathematical theoretical constructs, right? Okay. It's not physically possible to grind an optical lens down to where it's just a filament, right? Doesn't have physical dimensions. In the same manner, it's not possible to grind down a quadrupole magnet such that it's just a filament. But again, mathematical constructs, another tool from a mathematical toolbox, okay, a mathematical construct, all right, just to get a start on the situation. All right, so here we have the two thin lens matrix approximations of our quadrupole magnet. Okay, here we have it. Now, because it's a thin lens, which does not have a physical dimension, to make it somewhat reasonable, we have to insert what's called a drift space, which kind of gives it a physical dimension, okay? So here we go. All right. So here's the matrix for a drift space that needs to be inserted between the two 2x2 thin lens matrix approximations to the real life quadrupole. Just gets deeper and deeper, doesn't it? Told you. All right. So here is our drift space represented by a 2x2 matrix. Okay. So to get the thin lens approximation on the way of finding out what K is, we have to take this drift space and insert it. Insert it into the matrix equation for the thin lens approximation of a proton going through a quadrupole, all right? So here's the original coordinates. X naught prime. Remember, X naught is the horizontal position. And again, this is going to be a horizontally focusing, radially focusing quadrupole and a vertically or actually defocusing quadrupole. But so here, but we're talking about the horizontal radial. So here's the original position in phase space of that proton with respect to the z-axis and how fast that position is changing, how much is changing with respect to the proton's distance along the central z-axis, okay? You put it through the first lens approximation 2x2 matrix, right? Okay. And then it goes through the first drift space. And then it goes through the second 2x2 matrix, approximating the 4x4 matrix, okay? And then it goes through the second drift space. And when it comes out of that sequence, it has a new phase space horizontal or radial position, right? With respect to that central Z trajectory. And it has a new how much that radial or horizontal position is changing with respect to the proton's trajectory along the z-axis. Okay? Hey, Balo, what? What, Balo? Say hi, Balo. Hey, Balo. Balo. Okay. All right. Okay. So what we're going to do next, we're going to do some matrix multiplication. And I'm going to show you how that works. But we're going to leave that till next time. More linear algebra. Basically, what we have to do, we have to take these four matrices and multiply them together to get one matrix that you can see right there. And I'm going to show you how that's done, okay? Again, we're working our way towards that force constant K of a quadrupole magnet in a synchrotron. All right. In summary, so far, we have derived a 4x4 matrix that mathematically represents a physical quadrupole magnet, okay? And we have used many mathematical tools from our mathematical toolbox to get this far. And right now we're using linear algebra with matrices. So we have this 4x4 matrix that involves the force constant K of the quadrupole magnet. I know I'm repeating myself, but I just want to make sure because there's a lot of mathematics coming at you. And it's very important in order to be able to track the betatron oscillations of the protons as they circulate around the synchrotron. So we have our 4x4, represents the quadrupole. And to get a start on that K, that force constant, we split it into two 2x2 matrices, okay? That's what we did. Then we applied the thin lens approximation, which reduced things very much, okay? And in order to use that thin lens approximation, that 2x2 matrix, to make it physically reasonable, think of two filaments, right? One 2x2 that's radially or horizontally focusing and axially or vertically defocusing. And the other one that is radially or horizontally defocusing and axially or vertically focusing, right? Filaments, thin lenses that go back to that quadrupole, that 4x4 matrix, that quadrupole. And to make it reasonable, we have to insert a drift space, a 2x2 matrix that represents a drift space. We have to insert 2. Remember that? So now the next step in finding out the force constant of our physical real-life quadrupole magnet is going to be to do the matrix multiplication of those four matrices together to get a thin lens approximation of that entire system of quadrupole magnets, radially or horizontally focusing, axially or vertically defocusing, and radially or horizontally defocusing, and axially or vertically focusing. Okay. All right, so we'll continue on our journey. Remember, there's something in nature that is doing all this naturally. Okay? As cosmic rays reach Earth, there's something in nature that is naturally doing all of what we're trying to do here with our mathematical toolbox, right? And our particle accelerators like Fermilab. Something's going on naturally. Okie dokie. Tune in next week. Same fat time, same fat channel.